Hi, I'm DJ Ware. On this episode of the CyberGizmo, we're going to explore RISC-V. What is it? What is it all about? And what does it mean for us as consumers right after this? The RISC-V Foundation hasn't been around all that long. I remember, I think 2016, 2015, somewhere in there, they surfaced and they announced that they were working on a new spec that was going to be open. So whenever I hear of a new technology, the first thing, I'm so jaded, I always say, so what? Because, you know, in the truth of things, every company's desire is to lock in their users, they lock in their customers. They want to keep you on their platform. And that the companies make it very difficult for you to migrate away. Take, for example, Windows or Mac, the suite of applications that are available in the proprietary space, namely Microsoft Office and Adobe, all of the Adobe suite, and some of the database apps. Those are designed to hold you onto that platform, and they prevent you from being able to move away from, say, a Mac to Linux, because Linux doesn't have the proprietary software available for it. There isn't an Adobe suite that I'm aware of that's available for the Linux platform. There is some new tools that can be used for that, but I mean, if you look at like audio suites like Pro Tools, or you look at the video editing suites that are available in both the Mac and in the Windows environment, that level of sophistication just isn't on Linux. Sorry. So those hold people to those platforms, and that is part of the lock-in. Companies call this, and I've heard this term so many times, a rich ecosystem. That's what they're referring to as lock-in. And every time I hear that term, we have a rich ecosystem, red flags and alarm bells and red lights go off in my head, knowing that that is a sign that, watch out, this is how they're going to hold me to that platform. Companies are also profit-driven, duh. And so they only innovate what they need to do to hold you to the platform, to just enough to keep you happy. And it's quite a science inside of the marketing departments, and I know this, I've worked for many large technology firms over the past 40 years. It's a big science, and they spend lots of time figuring out the minimum amount of money to spend that will have the biggest bang for their buck, or the most return. That is either gaining new market share, if possible, or just doing retention of their customer base. So they carefully budget that innovation to fit in with their profit goals. And that's just how it works. I don't know how many times that I've sat in meetings with the marketing people, and they probably think engineers are the devil. The engineers think they're the devil. That's just the way it works. But when engineers come in with a proposal to do something new, marketing cranks it through this analysis of theirs, and they come back with an answer. And if it doesn't fit their profit motives or their profit goals, or it's spending too much money to develop, they say no, we're not going to do that. And I don't know how many times I've heard them say that they just don't think that this is a profitable thing to do. And so even though long term this may benefit them a lot, they don't look at long term. They don't care. Marketing people only care about the next quarter. They only look that far. 3 months down the road, that's all they care about. So that's basically how things work. They hold you to the platform, and they do the minimum amount of innovation they do to keep you there. The downside is that when companies finally get into a market where there is very little competition and there's no need to innovate, and we saw this with Intel when AMD just wasn't there to push them, they became complacent. They stagnated. I mean, how many times do you have to release a chip that's 14 nanometer, 14 nanometer, 14 nanometer plus, 14 nanometer plus plus, and 14 nanometer plus plus plus? They were just clocking up the CPU just enough. I know that if you look at the computer architectures from Skylake forward, even the i9 9900K, those are all. We'll talk about stages later, but they're all 14-stage processors, and all they're doing is reclocking them. So not a whole lot of innovation going on there. Now that's changed. Now that AMD is pushing hard on them a little bit, they are changing. So what is RISC and what is not RISC? I've heard a couple of places where they call RISC-V the open source CPU. No, absolutely not. It is not an open source CPU. It is an open source specification for the instruction set architecture, the ISA. So companies that develop the ISA are free under the specification. I've read it. They're free under the specification to keep it proprietary. Whatever they're implementing can be open or proprietary. It's their choice. But the specification has to remain open. And that is the rules of the RISC-V. Anyone can build a processor to support it, and provided, of course, you have the fabrication facilities to do it, or you know somebody that does. And there is a number of companies that are actively involved in it, and we'll talk about that a little bit later. So before we jump into all of the goodness about RISC-V, let's jump back for a second and talk about RISC. In the, I think it was mid-1960s, a researcher from IBM Labs and also University of California, Berkeley, were looking into the IBM researcher was interested in where did processors spend all their time? What instructions were most commonly in use during a run of an application? And so he went out and canvassed the users. I think he did some tracing on the machines and the applications that were running. And he came back with a short list that's these instructions, 70% of the time, are what is running in the processor. And the University of California, Berkeley, they went out and they actually invented RISC. So they took, I don't know if they took the research paper or they improved on the research paper or how all that collaboration worked, but eventually it culminated in IBM's 801 processor, which was the first RISC machine. And I think that was early 80s or something like that when it actually came to light. And also, Stanford University, they actually came up with the spec for the MIPS processor, which, of course, was the foundation of a lot of machines, including the Digital Equipment Corporation's VAX machines, the microarchitecture machines that Digital Equipment had as well. Also, Windows NT they had a RISC version that was based on MIPS. There's other RISC processors, but first of all, let's talk about what they are. A RISC processor executes an instruction in one clock cycle. So in contrast to CISC, a CISC instruction can take one to many clock cycles to complete because they're complex. They can be this long or this long or this long or that long in order to sit in the processor, and that might take several processor cycles in order to complete the instruction. But RISC by design is one instruction, one clock cycle. That is the definition. Also, RISC usually employs some form of pipelining. Pipelining is in the stages that you have. You have the instruction fetch. So the first thing the processor does is it fetches the instruction probably out of cache memory. It has to decode that instruction so that it takes it and puts it into the binary form that it needs to execute. And then it does an execute on that instruction. Then it usually does some sort of, some memory access if it's a move command or if it's an add command or if it's doing a store operation, then it has to do some memory access in order to do that. And then it writes back into the register, and the register then appears in the application. So the application can then take whatever value that was performed by that instruction and determine what to do with it. So the most common stages are the IF, ID, and EX. Some of the early machines that I was involved with only had 3 stages of pipelining. And now today, I think the Intel Core i9, well, actually, it's not just that one. It's all of the Skylake architectures. all of those machines are 14 stage. Now, what that means is, if you count that up, you'll notice there's only one, two, three, four, five. So there's 5. But if you have 14 stage, then you just repeat it, and you can have these stacked up. So I can be doing read ahead and figuring out intelligent branching to see what instructions I need to load next and have those ready to execute. So we talked a little bit about RISC. Where did it actually begin? So a lot of people say that Alan Turing's ACE, the automatic computing engine that was done in the 40s, in the late 40s, had many characteristics of RISC. There was the CDC 6600 that also was developed by Seymour Cray in 1964, had some characteristics of RISC as well. But the first computer, as we said, was the IBM 801, and that was in 1980. So CISC. CISC is complex instruction set. Now, it's not really fair to say that Intel's Core i5 and Core i7 and Core i9 are CISC because they're really hybrids. They do have some RISC features built into them, and they've had those features since the Pentium 5. So that has been a part of the core architecture, but generally speaking, the Intel architectures or the x86-64 is generally considered CISC. They have many different instructions, and if you compare the instruction set language between the RISC-V and the Intel, the current Intel reference manual for assembly language, which is over 4,500 pages long, they are orders of magnitude different. The RISC instruction sets are much less. The Intel CPUs are, of course, we talked about that being a hybrid, and that is because they do employ pipelining and some parallelism in the microencoded architecture. So, yeah, the CISC versus RISC debate's been going on for a long time. We'll talk about that at the end. That's not important for right now, which one is better. So RISC is dominant in the top 500 supercomputers in the world, such as the IBM Summit and the IBM Sierra. Those are the current 2 top machines as of June 2019. There are many companies that manufacture RISC chips. There's ARM, there's Qualcomm, there's Fujitsu, and on and on and on. And Samsung, of course, as well. But those architectures are all closed and proprietary. They require royalty fees in order to use them and to be able to license the instruction sets to build the tools that you need to actually use them. And that is about to change. So the top open source questions, many academic institutions have been creating RISC-V specifications. UC Berkeley is the originator. They're the ones that came up with the spec for the RISC-V. And they built this thing basically for academic use to teach students how to program machines. And so they kept getting queries from the outside world saying, hey, can we get this from you? And they were like, well, we're not really prepared to support it. So they formed the RISC-V Foundation, and they submitted their specification to that group. The spec covers both 32-bit, they support 32-bit, 64-bit, and 128-bit, architectures in their specification. And that is maintained today by the RISC-V Foundation. If you're a member, you can contribute to that specification. The open source specifications are fueling the chip development, and there's 3 versions of the spec. There's the unprivileged spec, the privileged spec, and then the debug spec. And the privileged spec has a couple of version numbers. There's 1.11 and 2.2. And as of June 2019, those were frozen. So now SOC development can begin as well as in earnest the CPU development. And so because they're free of worries about having it change out from underneath of them. Alibaba immediately took advantage of it, and in July 2019, they announced the XT910. I think it's Quanti, and that is a 12 nanometer chip. Now, most of the chips, if you look at like the Si5, Si5, those are built under academic specs. So the academic specs are always lower power, simply because they're basically the fabs are donating time to the university in order to produce them. And so they're not going to be the latest and greatest things. I think the Sci-Fi chip, which is an academic version, is a 22 nanometer spec. And I think they have an older one that's like 128 nanometer or something. But this one is a 12 nanometer, 16 core, 2.5 gigahertz CPU. It has 12 stage pipelines. It supports out of order processing, which means that, it doesn't care what order the pipeline occurs in. It'll reassemble it all back. So there's like a little table that it charts off. It schedule, the schedule, looks at the schedule, says, oh, this is done, this is done, this is done. I can now clear that. That's gone. To make sure that all the steps that are involved in that particular instruction set was completed. It supports 2 memory accesses per cycle, and that's pretty significant if you compare that to the CISC. I won't get into the hardware details. It's going to get way too deep. But in 2018, Alibaba had acquired C-Sky, and they're the makers of the Linux on RISC-V. It's a GX6605S. It's an older board architecture, so I suspect the reason for them acquiring that was to find a place to sock the XT910. Alibaba says that their chip is open source, so anybody can look at the code and anybody can look at how they developed it. They've also published some benchmarking scores, and as of end of July, they were way ahead in the performance areas in the RISC field, including ARM. They were way ahead. So the RISC-V specification is the same. Every company competes on the same level. Companies can use RISC-V, may be forced to innovate and simply by differentiating themselves. And so instead of the chip being the core focus, it will be the board. It'll be the I/O. It'll be the other tooling. It'll be software. It'll be the complete stack that actually forces them to innovate. And because there is hopefully a large field of competitors, that will force innovation to accelerate. So that benefits us because that protects us from the lock-in feature set. So we can freely move from one chip to another without having to worry about losing the applications that we like to run. Hopefully. So this is an old chart. This is from the first of the year, 2019. I didn't find one that's current, but it was talking about that they had 100 members. And you can see some very large names in here like NVIDIA, Western Digital, Samsung, Google, Microsemi, and there's IBM is in here. So there's some really large players in this group. Today they are saying they have as of the time of this video 365 plus members that are in the group. So there's a lot of interest in the community, and with this much interest, it's going to get very interesting. So I think in the coming years, it's going to get very interesting. There's quite a few companies that are slated to, over the next couple of years, to release RISC-V compliant CPUs, and there's quite a few of them that are coming in 2020. Linux is in the thick of it, of course. Both from the kernel development, they're in the 5.3 kernel. There is quite a bit of support, and that is maturing to support the RISC-V specification. And Debian, Fedora, Gentoo, OpenMandriva, OpenSUSE are all building the ports around it. So the tooling, like the compilers and the libraries and the desktop interfaces and all of the tools and the utilities that we use on a daily basis are being developed around that. BSD is also working on it. Both FreeBSD and also NetBSD are working on distributions to support the RISC-V platform as well. There's a lot of momentum going on, and I think this is going to spark a level of innovation that we haven't seen since the 80s. So, I mean, that's what I believe. And so one more thing, when you're comparing RISC and CISC, this goes to the debate. I don't know how many times I've seen this. They always compare clock rates. If you look back at the benchmark scores, if you go way back to when the RISC machines were coming in, like the MIPS machine and the Fujitsu machines, when they were in Motorola, the PowerPC, when you look back in those and you look at the benchmarks against Intel, they were just putting Intel under the table. And the clock speeds they were using were much lower. And the reason for that is the RISC process. Now, I got to be fair, benchmarks are one of those things where, liars, liars lie, and then there are benchmarks. But the thing about RISC and CISC is it doesn't matter. And so which one is better? It doesn't matter because the application the CPU architecture doesn't matter that much for the application. In the Linux world, if you're running on ARM or you're running on Intel, you have the same set of tools. And so that's the most important thing. It's the operating system, it's the compilers, it's the libraries, it's the utilities, it's the applications that you use on a daily basis. That's what matters. All this other junk is just fluff. So, I mean, the idea is to protect us from being locked in. And that is really the main thing. So if I want to use CISC, I can use CISC. And if I want to use RISC, I can use RISC. Or I can float an application back and forth between them. That's really the power of freedom. And that's what we're really talking about. So one of the things that I saw this and I was just totally, I was just gobstopped. This is the RISC-V specification supports up to 65,536 cores. Wow. Yeah. What Dorothy said, Toto, I have a feeling we're not in Kansas anymore. So I hope you enjoyed this today. And I look forward to working on the next video and hope to see you there. If you would, please like and subscribe. Hope to see you again real soon, and bye for now.